click on ISE Xilinx Design Suite 14.5. This is the GUI of this window. If this some project is already open, we'll go to File and we'll close the project. And now this is how that GUI actually looks like. Now we'll create a fresh project. So first we'll click on New Project. We'll give some name to this project. Suppose if you're designing a half adder, let me give some appropriate name. Make sure you have created an appropriate folder and see to it you know the location of your folder. Click next. Before going next, please check out this top level source file. It has to be Hdl since we are going for Vhdl. Click next. Here we'll have to make a mention of the tool, or rather the board that we are using. In our lab we have been using Spartan 6, so we'll select Spartan 6. Choose the device name, the package and the speed looking into that board. See to it your preferred language is Vhdl and the synthesis tool is XST. Once again click next, finish. So now on the left hand side you will see your folder, the name that I had given half adder. Below that you would find your board name, the FPGA board. This is the nomenclature of the FPGA. Now we'll create a Vhdl module under this project. So right click on the project name, click on new source. Here since we are creating a Vhdl module, we'll select option number 6, Vhdl module. We'll once again give a specific name. See to it your project name and file name are different. While giving file name, we have to take care of 4 things. 1. The file name that you are giving should not be a Vhdl keyword. Second, it should not have a space in between. Example, as I have used half adder, I cannot give half space adder. I cannot use any special character, so it cannot be half plus adder, half dash adder. Fourth, I can only use underscore, so it can be half underscore adder. So let me name it as h_a. Ensure that your location is chosen. Check that add to project is checked so that it would automatically get into your project. Click on next. Now here you are supposed to give the port names. In our design we have got 2 inputs, so A, B. The directions, since they are input ports, the directions would be in. Since these are 1-bit data, I'm not gonna use MSB or LSB. Example, if it is 4-bit data, then MSB would be 3 and LSB 0, since we write 3 down to 0. After working with the inputs, we'll move towards output. So one would be sum, the port would be out now, direction, and the next would be carry, direction would be out. Once inputs and outputs are given, we'll once again click on next and then finally finish. So now on your screen you will see your code partially written. The lines that you see in green are the commented lines. This is our library, and below that IEEE.std_logic_1164 is the package. Next we go for entity. The name of the Vhdl module will be reflected as the entity name. The port names that I've given would be visible in my entity. Next I'll have to write my architecture. In architecture we have 3 modeling styles: behavioral, structural or data flow. So depending on the need you'll have to choose the appropriate modeling style. Here we are going for data flow modeling, so I'm using the concurrent statements. Once you are done writing the code, on the left hand side you will have to check if your code is syntactically correct. So for the towards the left hand side you will see an option synthesize. Open up the options within synthesize. You'll see an option check syntax. Double click on check syntax. Save your code. If it shows a green tick, it means your code is syntactically correct. After that, I will check the RTL schematic of our design, if our code is synthesizable or not. So we'll go to option number 1, view RTL schematic. Click OK. Here, rather than going for Explorer Wizard, we'll select, since we are supposed to see the schematic of the top level design which are half adder, we'll select option number 2 and then we'll click OK. So this is how your top level module half adder looks like, which has got 2 inputs and 2 outputs. If I want to check what hardware is needed for designing this, you can double click inside this box, and it now talks about the gate level implementation of your design. So as visible, it is needing an AND gate as well as an XOR gate. If I want to come back, here you'll see 2 green buttons, one towards left and one pointing towards right. So coming back to the previous schematic, you can click on this. Going inside, this is how you can navigate between the windows. After my check syntax is done, after the schematic has been designed, we will move towards the implementation of our design. But to implement, I need to map my design with the FPGA pins that are available. So before that, we'll be creating the Ucf file. To create Ucf file, we'll right click on the .vhdl file, click new source, and now select option number 3, implementation constraint file. Through this, we are gonna create the Ucf file for the intended design. Give an appropriate name. Next, finish. So now blank editable window would come up. So the pins that you need to be mapped, you can very much make a mention on this Ucf file. Once you write down the pin numbers, you can save that Ucf. See, now inside your .vhdl file, that Ucf file is visible. You can save the file, and then we are all set to move towards the final implementation. So once again, see here the options are not visible. The options are related to .vhdl file, so we'll have to select .vhdl and all the options will once again come up. Now we'll implement a design. Double click onto it. All the 3 options are checked, translate, map, place and route, we need to create the .bit file. So that is created using the option generate programming file. So right click on generate programming file and click run. Once this is tick, it means your .bit file has been successfully created. Now we'll click on the next option that says configure target device. After creating the .bit file, that needs to be dumped onto the target FPGA board. For that, under configure target device, you'll see two options. So we have to move or go ahead with the next option, manage configuration project, impact. So double click on impact. Once you do that, a new window would pop up, wherein, as we know that my FPGA operates on the boundary scan mode. On the left hand side, you'll see the first option, boundary scan. So double click on boundary scan. A blank window would come up. Onto it, right click. Check the first option, add Xilinx device. Double click onto it. Now it is asking which bit file you need to download onto your board. So as chosen, we had created our Vhdl file h_a, of which it has automatically created the .bit file. So select the .bit file, click open. Now you have the target device as well as the target bit file in front of you. So now it's a matter of just of downloading. Right click on that gray box Xilinx and click on the option program. Now it has identified the cable, and then once your kit is attached to your computer through the USB port, it would show program succeeded if your program is successfully completed. So that's all about the implementation part. While designing, we have got one more option, which is of simulation. So I'll quickly take you through how simulation is done. We'll close this. Right, so if you see on the top, you'll find two check boxes. One is implementation and one is simulation. This flow is of complete simulation, but if I need to check if my code is functioning correct or not, I'll have to click on the option simulation. And then for checking the code, I will have to create a test bench for the same. So for creating a test bench, to your left hand side, you have a .vhd file. Right click onto it, click on new source, and now select Vhdl test bench, the second last option. Give an appropriate name to it. Next, and finish. Once you do that, your test bench would be partially available on your screen, wherein again we have the library, package, entity without any ports. We have the architecture, within which your main design half adder is now a component. All the signals that you need will be now the internal signals, as visible A, B, sum and carry are the internal signals. We don't want a clock here since it is a combinational design. So we have commented the clock part. Moving ahead, this is the port mapping of our design. Again we see a module which operates on clock, since a combinational design will eliminate this part. And now we move towards the actual design. So this is the main process begin, wherein we'll just be assigning some random values now. Let me assign a value. We'll wait for some stipulated amount of time. So for this duration, my A is 1. Let my B be 0. So by doing this, I am checking the combination 1 0. Let me wait for some time to generate the output, and after that we'll change the combination. This you can do for all the 4 possible combinations. I am doing it for these 2 combinations. Since I want to execute it just once, I'll write wait. Once your test bench is done, you have to click on save. See to it your simulation option is checked. And now this file is visible under your main VHD file. At the bottom you'll see an ISIM simulator. Select this test bench file and go to check if your code test bench code is syntactically correct or not, you can click on the first option, behavioral check syntax. So that would help you in finding if your code is syntactically correct or not. So this green tick indicates the code is correct in terms of Vhdl syntax. Next, to check the output, we'll click on the second option, simulate behavioral model. And this is where your output window would come up. So whatever is your output would be visible on the simulation window. Once you are done, you can exit. So, and further to move back to the implementation, you can check the option implementation, and then you can see the output on your board. That's all for today. Thank you.